She's visiting us from, let me make sure I get this name right, the Cooperative Institute for Severe and High Impact Weather Research and Operations. It was formerly known as the other CiMMS. It's a collaborative group between NOAA and the University of Oklahoma. Dana's doing her postdoc there, and she graduated with her BS, MS, and PhD from Penn State with her PhD in December 2020. And she's been working primarily with radar data and some of its broader applications to winter precipitation. And we're looking forward to your talk, Dana. Welcome.
All right, thank you for the introduction. You can hear me and see me okay, right?
Yep, all good.
Okay, all right. Yeah, again, thanks for the introduction. I was hoping you'd read this long title for me. But anyway, so the title of my talk is A Multifaceted View of Winter Precipitation, Societal Impacts, Polarimetric Radar Detection, and Microphysical Modeling of Transitional Winter Precipitation. So this work that I'm going to show is primarily everything that I've done from Penn State. So unfortunately, I don't have too much new stuff that I'm going to show today that I've been working on for my postdoc, but I'll talk a little bit about what I've been doing the last year. So for this project, my PhD advisor was Matt Cumgen. A couple committee members that I would like to acknowledge are Eugene Cleo, Jerry Harrington, and Vikash. A couple other collaborators are Alan Black, who helped with the societal impacts portion of the work, and both Mariko and Pavlos were kind enough to provide some radar data for the observational portion of my work. So the first thing that I need to do is actually define what we call transitional winter precipitation. And that's defined as any and all of these precipitation types. So freezing precipitation, freezing rain or freezing drizzle, ice pellets, or as it's colloquially known as sleet, mixed phase hydrometers, which include both liquid and ice masses in a single particle, and also precipitation type mixtures as being rain and snow, snow and ice pellets, or any combination that you could possibly think of any of these precipitation types. So the big picture that kind of ties all these three seemingly separate elements together is to address each of these questions. So for the societal impacts, we want to know what the risks are associated with these precipitation types. For the polarimetric radar detection portion, we want to know what, if any, are the polarimetric indicators of each of these precipitation types. And then for the microphysical modeling component, we want to know what processes are occurring and also which processes are responsible for the observed radar features. So the motivation behind this project is that transitional winter precipitation tends to be kind of overlooked or neglected in studies, as they typically occur between regions of rain and snow, and they occur with very limited spatial and temporal extent. And also a variety of precipitation types can result from very small changes in the low-level temperature profile. And these small changes can actually dictate whether melting or refreezing is a partial or complete process. And it can also be very difficult to identify or forecast the location, time, and extent of these precipitation types. So obviously they can cause significant damage for infrastructure and vegetation. They can be very hazardous for the aviation community. It can cause delays, but also presents significant issues such as in-flight icing. And then for motorists, for pedestrians, it can be very hazardous and cause slips and falls and injuries. But then obviously for motorists, it can be particularly dangerous, which is going to be the focus of my work for the societal impacts portion, because it can result in loss of control, injuries, fatalities associated with these collisions during winter weather. So the best case scenario for motor vehicle crashes is that winter precipitation can actually reduce the traffic volume and reduce vehicle speeds so that when crashes do occur, they would be less severe. So fewer injuries and fewer fatalities associated with them. However, the worst case scenario is that it actually increases the number of collisions, injuries, and fatalities that occur. So for example, precipitation results in a 75% increase in the collision risk and also a 45% increase in the injuries that occur. So the FARS, or the Fatality Analysis Reporting System, is a national census of fatalities that result from motor vehicle crashes. And this database includes the date, time, location, number of fatalities, atmospheric condition, and all sorts of other variables related to the crash in that database. So the atmospheric conditions include precipitation types. So prior to 2013, the only precipitation types were rain, snow, and sleet. However, in 2013, they added the freezing precipitation code. So this actually allows us a unique opportunity to investigate the fatalities that are occurring during each of these separate precipitation types. So here I've tabulated the total fatalities that occurred between 2013 and 2017, as categorized by the precipitation type that is identified by first responders that are on the scene. And so you can see that about 15,000 fatalities occurred in that period during any precipitation type, with the majority of them being during rainfall. However, there were 2,211 fatalities that occurred during snowfall and 343 that occurred during sleet, compared to only 108 occurred during freezing rain. And this is a little bit curious because there seem to be over 3 times as many sleet fatalities than freezing rain fatalities. And this is a little curious because we're typically under the assumption that freezing rain is more dangerous, and the fact that freezing rain occurs more frequently and typically lasts longer than sleet. So it's interesting that there are fewer fatalities during freezing rain. So the question now is why this could be the case. And one reason could be the over-reporting of sleet in this database. And this could arise for a couple of reasons. One being that the definition of sleet can kind of be a little murky. We want the definition of sleet as being ice pellets. However, colloquially in the US, unfortunately, it can be referred to as the rain and snow mix, which is not what we want to investigate here. And there could also be some human error. So for example, ice pellets and grapple tend to look fairly similar to a layperson. So they could be mistakenly reporting ice or sleet when they really mean grapple or snow. So another reason for the discrepancy could be that there would be an underreporting of freezing rain in the database. This could result from not all states having a freezing rain option in the crash report, or freezing rain could potentially be occurring less frequently on roadways as a result of warmer surface temperatures, or the result of spreading treatments such as salting on the roadways that could reduce refreezing. Another reason could be that the crashes that occur would be less severe when they do happen. So obviously fatality counts alone can't tell us the actual impact of precipitation on crashes, obviously because of these precipitation type biases in the database, and also because it doesn't actually account for the exposure of a motorist to the different hazards. So for example, the frequency and duration of precipitation types is kind of buried in with the total bulk numbers of fatalities. So in order to account for these influences, we want to determine the crash risk. To do so, we compare the odds of a crash occurring during a precipitation type of interest versus the odds of a crash occurring during a similar non-precipitation period. So for this project, we got data from, we got crash data from Kansas for a 20-year period. And so the first thing that we did was actually confirm the precipitation type that's reported in the crash database with nearby meteorological precipitation reports. And then we determined the beginning and ending time of the precipitation reports. And we found a comparable non-precipitation period with at least one crash that occurred. And this comparable period had to be the exact same day of the week, the exact same time of day, a very similar location and season. And what we did was then compare the crash counts as an odds ratio between the two periods. So here I plotted the crash risk estimates for each precipitation type For property damage only crashes in the light blue, injury and or fatality crashes or casualty crashes in the dark blue. And what I've plotted here is that the bars are means, the mean estimate for the crash risk, and then the lines corresponding to them are the 95% confidence interval. So I've also plotted the 1.0 relative risk estimate, and this actually would imply that the crash risk is the same during the precipitation as compared to the non-precipitation period. So what you can see here is that for rain, snow, sleet, and freezing rain, all crash relative risk estimates are greater than 0, which implies that each of these precipitation types increases the risk of motorists to have these different crashes. So if we focus on the property damage only crashes, there's a statistically significant increase in the crash risk as we go from rain to snow. And then again, a statistically significant increase as we go from snow to freezing rain. But then for the risk estimates during sleet, these values actually encompass values of snow and freezing rain. So we can't say anything about the statistical significance of this other than that it's greater than the risk during pure rainfall. Same thing for the casualty crash risk. There's an increase as we go from rain to snow. But then there's also a higher risk as we go from rain to freezing rain. But there's not a statistically significant difference between snow and freezing rain for these casualty crash risks. And then again, for sleet, these values are encompassing values for rain and sleet and snow and freezing rain. So we can't say if there's any sort of hierarchy in precipitation type for these crash risks. So the implications of this is that there is some sort of risk hierarchy with precipitation type. So again, property damage only crashes, freezing rain is greater than snow, which is greater than rain. And then for casualty crash risk, again, freezing rain and snow are both greater than the risk during rainfall. So now that we've established that the crash risk actually has a dependence on each of these precipitation types, but then before I go into the other aspects of the project, I want to kind of piece together the basic microphysical processes that are responsible for producing each of these precipitation types. So if we start with snow aloft, the first question is whether or not there is melting. So obviously if there's snow with no melting, that's going to produce snowfall at the surface. However, if there is melting, the next question is whether or not there is refreezing. So if snow melts and there's no refreezing, that's going to be rain. But then if there is refreezing, the next question is where is this refreezing occurring? If it's occurring aloft, that will produce ice pellets or sleet. Whereas if that refreezing is occurring at the surface, that would produce freezing rain. So obviously this is like a super simplified version because in reality we can get an entire spectrum of particle types based on the different degrees of melting and refreezing that occur. And also it can get more complicated as, across a distribution of particle sizes where perhaps the smallest particles melt completely, whereas the larger particles don't melt as completely. So the remainder of the talk is going to focus on the melting and refreezing processes that are responsible for producing ice pellets. And obviously this is a small subset of all the different transitional winter precipitation types we can get, but it can have important implications for the other precipitation types. So for example, if we can improve our understanding of ice pellets and distinguish it from freezing rain, that can just help us distinguish it from freezing rain and from snow to be able to isolate which precipitation type is occurring. So just so everyone's on the same page, when I say refreezing, I'm actually just referring to the freezing of fully or partially melted hydrometeors. And this is the process that's responsible for ice pellet formation. So here's just a quick schematic of the two separate ways in which ice pellets can form. So obviously, again, we begin with snowflakes that start to melt. And then on the left part of this diagram, if these snowflakes fully melt, once they encounter a surface layer that's less than 0 degrees Celsius, they don't start freezing right away. They have to first nucleate. So this is occurring at some colder temperature at a lower height than the wet bulb temperature of 0. However, if these snowflakes melt only partially, they still contain an ice nucleus around them, so they can start to begin refreezing at a higher height at wet bulb temperatures of 0 degrees Celsius. So before getting into the polarimetric radar detection of ice pellets, I want to do just a very quick overview of some, not all, just some of the polarimetric radar variables. I'm also going to discuss how we're going to actually interpret these variables, with the caveat being that we're assuming that the particles are going to be small compared to the wavelength of incident radiation, which is going to be true for most of the data that I'll be showing for this talk. So radar reflectivity factor at horizontal and vertical polarization, or ZH and ZV, is proportional to the amount of power that's received by the radar, and it's related to particle number concentration and particle size distribution. So if we have more particles or larger particles, that's going to increase ZH and V, but it's also related to particle composition, where ZH and V of an ice particle is less than ZH and V of a liquid particle of the exact same size and shape. So what happens if we take a liquid drop and start to freeze it into an ice pellet? That is going to decrease ZH and V, whereas the opposite is true if we melt that ice sphere into a liquid particle. So differential reflectivity, or ZDR, is the log difference between the horizontal and vertical radar reflectivity factors, and it's related to particle shape. So if a particle has its major axis aligned horizontally, that's going to be a positive ZDR. Whereas if the particle is spherical, or if it's tumbling, that's going to appear spherical to the radar. So ZDR is going to be about 0 dB. And ZDR is also related to composition. So ZDR of an ice particle is less than ZDR of a liquid particle of the exact same size and shape. So linear depolarization ratio, or LDR, is the log difference between the radar reflectivity factors at vertical and horizontal polarization when the particles were illuminated only by a horizontally polarized radiation. So if particles are non-spherical and they're also at an angle relative to the incident radiation, they can actually depolarize the incident radiation and scatter in the orthogonal direction. So the top set of particles are obviously non-spherical, and they're also at an angle relative to the incident radiation. So LDR is going to be greater than negative infinity, or greater than 0 in linear terms, whereas the bottom set of particles are spherical, or they are parallel or perpendicular to the incident radiation. So they do not depolarize any of that incident radiation. So LDR is 0 in linear terms, or negative infinity in logarithmic terms. So this is also related to composition, where LDR of an ice particle is less than LDR of a liquid particle of the same size, shape, and orientation. Okay, so now that we've gotten all that out of the way, I want to focus again only on these 3 variables, but we're going to relate this back to refreezing and how we expect these variables to change. So we should actually expect reductions in both ZH and ZDR, because we're going from liquid to ice particles, and also because we typically get an increased wobbling or tumbling of particles with freezing. So that is going to decrease ZDR and ZH. So in reality, this is not quite the case. So here I've plotted a vertical representation of the polarimetric radar variables at side incidence during an ice pellet case. And we can see that within the wet bulb temperature less than 0 degrees Celsius surface layer, there is this reduction in ZH as we expect. However, there's this unexpected enhancement in ZDR, which kind of begs the question as far as why we are seeing this. And the truth is that we don't actually know the answer 100% for this. So the hydrometers that we observed in that case were fully melted prior to refreezing as a result of them starting to refreeze at lower temperatures, typically around the -5 degrees Celsius range. So the most probable hypothesis for this observation is that there is a preferential refreezing of the small drops. So doing so would actually increase the relative contribution of the larger drops to ZH. And these larger drops have intrinsically higher ZDR because they tend to be oblate due to drag influences as they fall. So in order for these smaller drops to freeze first, they have to be nucleated at about the same time as the larger drops. So this could actually result if there is only partial melting of the particles. However, as I said before, that we observe these particles to be fully melted, so this is not the case as far as why these smaller drops might freeze first. However, if they're fully melted, one hypothesis is that there could be locally generated ice crystals that nucleate via contact nucleation. And if it's not this nucleation mechanism, there has to be some sort of other mechanism that's occurring at -5 degrees Celsius. But there's a lot of uncertainty as far as what could actually cause this ice nucleation, so I'm not going to get into that too much, and we're just going to look at the implications of hydrometers freezing at this temperature. So as far as new observations, we have data from the Casper radar, which is a fully polarimetric and Doppler radar that's at the Stony Brook University. And we have data from an ice pellet and rain event that occurred on 17 December 2019. And again, I've plotted ZH and ZDR here in the same manner as before. And we can see that there is that reduction in ZH. But then in this case, there is a reduction in ZDR as well that's corresponding to that. So now we need to know, why is there the enhancement in the other case, whereas in this case, we are actually getting that reduction in ZDR as we would expect. So here I've plotted the 30-second averaged spectral Z on the left and spectral LDR on the right. And it's plotted within each velocity bin, but values, bins with return power less than -80 dB have been filtered to remove some noise. So these spectra are obtained when the radar is pointing vertically. So there's information on particle fall speeds and also the polarimetric radar data that's collected as these particles are falling in each of these velocity bins. So the convention that I've plotted here is that increasing negative values are corresponding to increasing fall speeds. So what we can see here is that there's melting indicated by both an increase in Z and LDR as that liquid mass is increasing in each of these particles, and also as an increase in the particle fall speeds as these light and fluffy aggregates melt and their density increases to be more raindrops. So when that happens, their fall speeds adjust closer to those of raindrops. So in this teal region, we've identified that there are partially melted snowflakes. And we know this because there is elevated Z and LDR values within this region, which indicates that these particles haven't actually collapsed into raindrops. Because if these particles did collapse, they would appear, if they were raindrops, to be spherical from below. So that would result in very low LDR values. And LDR for this radar would be at the -30 dB range, because that's the system lower limit of the radar. However, if we assume that they are just melting aggregates, from below, they tend to have this irregular shape, and they also have no preferred orientation in the horizontal plane. So LDR would remain elevated in this case. So in this pink region, we suspect that there are liquid drops because LDR is actually low. But we could also have some partially melted snowflakes in here because we do see a slight continual reduction in LDR as we get closer to the surface. So that could indicate that there's either further collapse going on, or there could be some refreezing in this area that would also reduce LDR. So in this purple region here, we actually have the refreezing of those partially melted snowflakes because we see this decrease in Z and LDR. And these decreases are occurring within the slower falling particle bins first. You can see based on this curve, this bin is freezing at a higher elevation than the larger bins. So that indicates that these smaller particles are freezing first. So what we could imagine from this case is that because they're partially melted snowflakes that are refreezing, that you could imagine that the ice pellets would be more of these irregularly shaped particles. So if we go back to the polarimetric profiles that I showed earlier and kind of match them up to the spectral data that we have, we can see that the reductions in Z and ZDR actually correspond with that transition region from the teal into the purple. So we see that those changes are associated with that preferential refreezing. But again, there's not this ZDR enhancement, even though there is this preferential refreezing. So the results of these observations are that there is that preferential refreezing of the smaller particles. But again, there's no ZDR enhancement. And the reason for that is that these larger particles aren't liquid, like as that preferential refreezing theory kind of proposed. So instead, they're semi-melted and non-collapsed snowflakes, whereas again, the enhancement was thought to depend on the presence of large liquid drops. So what we know from the observations so far is that a ZDR enhancement for refreezing is present for the refreezing of fully melted hydrometers, but we don't know why just yet. And then for the refreezing of partially melted hydrometers, there is no ZDR enhancement, and this is just the result of basic refreezing arguments as we're going from liquid to ice particles. So now we're going to see if we can get a better sense of why we're getting this ZDR enhancement for the fully melted particles using a microphysical model. So to do this, we just performed a very simple refreezing test using a scattering model by sequentially refreezing a liquid particle distribution bin by bin. And with each new frozen bin, we recompute the polarimetric radar variables at S-band. This actually simulates the preferential refreezing of these small drops because we are refreezing the liquid distribution from small to large drops. So this test was actually performed in Cumgen et al. 2013, but we're just going to repeat it for the particle size distribution that I am going to use for the rest of the test after this. So the assumptions are that the particles are oblate spheroids with an axis ratio of equivalently sized raindrops with a mean canting angle of 0. So these particles are typically falling with their major axis aligned horizontally. And we also assume that the angular canting angle distribution width changes. So for raindrops, these particles tend to be more stable. And then ice pellets, the canting angle distribution width is 40 degrees, which indicates that these particles are wobbling just a bit more than the raindrops. So just to exemplify the concept, if a particle has a narrow canting angle distribution, it's more stable than if it has a wider canting angle distribution, so it's wobbling significantly more. So here is the particle size distribution that we chose for these tests. This is chosen from Gibson et al. 2009. They had an ice pellet particle size distribution so that we've discretized into 0.1 millimeter increments from 0.1 millimeters to 4 millimeters. So again, we start with a liquid drop distribution. We freeze the very first bin and then recompute those polarimetric radar variables, and then keep freezing the bins and recomputing the variables until the entire distribution is frozen. So here is the ZDR values for as a function of the number of bins frozen. So on the very left of the plot is the ZDR of that distribution being all liquid with no frozen bins. And then on the right part of it is the ZDR value for that distribution if it was an all ice particle distribution. So we can see that doing so creates a maximum ZDR enhancement with particles less than 2.8 millimeters being frozen, and then the larger ones remaining liquid. So what happens is if we kind of rotate this plot vertically, this is approximately what we actually expect the enhancement to look like in height, where we begin with an all liquid distribution. We freeze the smaller particles first, and then we get this enhancement prior to all the particles being frozen. So obviously refreezing is not occurring bin by bin. It's actually a more gradual process across a particle size distribution. So to kind of step it up another level is we want to actually create a microphysical model to simulate the refreezing of a liquid drop distribution more accurately. So we take an idealized one-dimensional steady state precipitation column, and we assume that these particles are freezing radially symmetric. So we start with a liquid sphere, and as it's freezing, it forms this ice shell that grows radially inward to form the ice pellet. So we couple this microphysical model with a polarimetric radar forward operator to actually simulate the polarimetric radar profiles. And we changed the particle shape to just assume that these particles are oblate spheroids, with the axis ratio of the inner core being equivalent to that of the particle exterior. So in the microphysical model, these particles are spherical, but then in the polarimetric model, we kind of squish those particles a little bit to get more of that realistic shape of the particles. So we take the same liquid distribution that I showed before, and I'm nucleating drops at the -5 degrees Celsius layer in the this assumed profile from Haynesack and Stewart, 1995. And so then on the right, we have the liquid water mass fraction within this model, where the dark gray signifies that the liquids, the drops are completely liquid, and then the light gray means that they have completely frozen and that they're ice pellets. And then the blue would be mostly still liquid, and then the yellow would be mostly ice. So what we see is that we have a very quick transition of the smaller particles to solid ice pellets, whereas the larger particles still actually have some remaining liquid in them as they fall to the surface. So the results from this, unfortunately, were not very exciting. So we got that ZDR reduction, or that ZH reduction, but we were not able to simulate a ZDR enhancement using this model. But that's okay, because we know why. The reason was that the reason was because of that ice shell that's forming on the large drops, which has a decreasing effect on ZDR that's actually overwhelming the increasing effect of the oblate shape of these particles. And this is different from that simple refreezing test where I kept the very large drops liquid. So in this case, now we form that ice shell around them. So now the question is, what if that ice shell is not actually symmetric around the particle? And this is actually realistic because we do get more favorable heat transfer on the bottom of a particle owing to ventilation effects. So here I've taken a picture from Murray and List, 1972, and kind of enhanced the colors on it a little bit so you can see that thicker bottom ice shell as opposed to the very thin top ice shell. So we actually only get symmetric ice shells forming if these particles are actually tumbling as they fall. But then we don't actually know if all ice pellets actually do tumble or wobble more as they're falling. So this process could actually be realistic to what we're observing, especially when these particles are just starting to freeze. They might not have increased their wobbling enough to offset this asymmetric ice shell. So in order to approximate this effect in the model, we're going to model the inner spheroid as having a lower axis ratio than the exterior. But again, we're limited by a concentric spheroid scattering model. So to do this, we just distribute that liquid core more along the major axis, which simulates a thicker ice shell on the bottom. But unfortunately, it also simulates a thicker ice shell on the top of the particle. So this is obviously increasingly unrealistic as the particle freezes more. However, the results of this was very promising. So again, the right part of this slide here is the same as before, because we're not changing anything with the microphysical model. It's only the polarimetric operator. So we are seeing that we do actually get this ZDR enhancement with this change in the assumption. And the reason for this is because we're distributing that liquid core, which is contributing to an increase in ZDR that's overwhelming the reduction of the ice shell that's having on ZDR. But then obviously we are getting that reduction in ZDR once a significant portion of the particle size distribution is frozen. So another thing that we can kind of play around with is we actually went back and changed the assumption that particles are increasing their wobbling. So obviously, if these particles are increasing their wobbling or tumbling as they're freezing, that's going to kind of offset and restore that ice shell symmetry. However, if we assume that there's no increase in the wobbling, these particles tend to still be more stable. So the physical implication is that the ice shell asymmetry would be increased. So that way, it actually produced an even greater ZDR enhancement that's closer to observations that we've seen. And the result from this is because we're actually just distributing that liquid core more along the horizontal, and that's more stable. So that's increasing ZDR even more. So obviously, there's significant limitations to this. The degree of ice shell asymmetry is unknown. It could be a function of size, liquid water mass fraction, or the freezing rate itself. And we also don't know what a realistic inner core shape and position could be. And we also don't know what the canting angle distribution is or how it changes with refreezing, if it changes at all. So the conclusion here from the observations is that the refreezing of partially melted and non-collapsed snowflakes does not produce a ZDR enhancement. But then in theory, the preferential refreezing of small drops should produce a ZDR enhancement. But then in nature, that preferential refreezing is not sufficient. So other factors that could increase ZDR are the presence of asymmetric freezing of the ice shell or potentially minimal wobbling. So the implications here are that there could be two different polarimetric features associated with refreezing. One being that there's no ZDR enhancement for the refreezing of, there is a ZDR enhancement for the refreezing of fully melted particles, but then there's no ZDR enhancement for the refreezing of partially melted particles. So potentially the presence or lack of a ZDR enhancement during an ice pellet event could indicate the particle species that are undergoing refreezing and also potentially suggest the height of refreezing. So if we go back to the schematic that I showed earlier, but just kind of focus on that lower layer of the closer to the surface, we can see that on the right here, we have partially melted particles that are freezing. So there's no ZDR enhancement in this case. However, on the left side, with the refreezing of fully melted particles, there is a ZDR enhancement that's at some lower height than the 0-degree wet bulb temperature height. So obviously this can have very important implications for aviation because particles have already started to refreeze on the right part of this plot. So it should be a lot safer for aircraft to fly through than within the left part of the of the diagram where we do actually have super cool liquid drops that can actually cause significant problems for the aircraft, such as freezing on the airframe. And also for higher elevations, the scenario on the left could mean that there is freezing rain as you're driving, whereas on the right portion, it doesn't get that ice glaze that's forming on the roadways. So this distinction could be important for surface transportation issues, because the cars on the left would be exposed to a greater crash risk than the car on the right side. So future work is that we want to look at crash risk estimates across the US, not just in Kansas. Kind of see if that hierarchy with precipitation type holds true in other states, or if it's just limited to that region of the US. We'd also like to see if the distinction holds true in other cases on the polarimetric radar side of things, for that the ZDR presence during fully melted versus partially melted hydrometers, and maybe if there's limitations or caveats to what I've shown. The last thing is that we want to know a little bit more about these ice pellets and their behavior as they're freezing. Are they wobbling? Is there this asymmetric freezing that's occurring to produce the ZDR enhancement? So obviously the ultimate goal here is we want to improve the detection and forecasting of transitional winter precipitation, and also increase driver awareness of the hazards associated with them. And we want to ultimately reduce the societal impact of them. For example, resulting in fewer crashes or less severe crashes if they do occur. So I didn't get a chance to talk about what I've been working on in my postdoc, but just a quick little overview. I've been looking at changing weather conditions leading up to fatal crashes, and also National Weather Service messaging of the weather conditions surrounding fatal crashes, and also the impacts of precipitation type, intensity, time of day, and so all sorts of other variables on the traffic volumes, so how many cars are actually on the roadways, and also those effects on crash risk for motorists. So that's all I had, and I will take questions.
Thank you. I want to give a chance for students to first ask some questions of Dana. So you can either use the raise hand feature or type it into the chat and I can read it off. So I'll just give like 30 seconds to collect your thoughts and either raise your hand or put in chat. But we'll let students go first if you have a question.
And I can see the chat if someone has a question, but I won't be able to see the YouTube version if there is something. I think we've discussed that before.
Yeah, Pete said he'll put it in the chat if it's there.
Okay.
So any questions from students? Okay, we will open it up to everyone, but students feel free to chime in at any point. So anyone who has a question for Dr. Tobin, Grant, go ahead.
I did. I really enjoyed this talk, and I really like the connection between the practical application to safety all the way down to basic precipitation physics and radar. I'd like to kind of return to this conundrum with the refreezing droplets, because it seems like a really hard problem, and you're taking an approach which is very appealing in the sense that we understand that the heat transfer is at the surface, and so you kind of want to have a shell of ice forming around it. And of course, it's also nice to be able to apply a computational method that works for concentric spheroids, which the shell approach allows. But I guess I'm wondering, there's a theoretical question I have about that, and there's an observational question. The theoretical one is that if you have a partially melted particle that still has some residual ice in it and it begins to freeze again, will it freeze from the outside inward, or will it start freezing where that ice particle is already located and grow outward from that location? in which case you wind up with more of a slush than a shell. That's kind of the theoretical question. And then the observational one is whether anybody has actually observed refreezing droplets that have a shell of ice that's surrounding the core of liquid water, because it seems like, in my own experience, I haven't seen that, but I don't know whether other people have or not. So I'm just wondering whether the whole idea of a shell around liquid water might need to be revisited in terms of how often that actually happens.
Yeah, so I thought I had a picture. I know Matt took a picture where it was literally an ice shell, and then everything inside of it was slushier.
Okay.
And I know I have seen, I think it's like some paper from Hallett and someone else from like the 70s or something. They had a picture where it was the ice shell and the slushy interior for them. So I know that it is more energetically favorable to form that ice shell. But I do concede that we have no idea how particles are freezing if there is still that existing ice core. So unfortunately, what's happening in microphysical models is that no matter what, they're defaulting to producing that ice shell. Instead of growing the ice core, they're just freezing from the outside in anyway. So that can actually result in different heights and depths of the refreezing. So I took a look at that a little bit, but sorry, I'm getting a little off track. But yes, to answer your question, we do not know how prevalent refreezing from the inside out is. We just know that if it is a fully melted drop, when it refreezes, it will freeze and form that ice shell and freeze from the outside in. That's consistent with lab studies and observations. So hopefully I think that answered both your questions.
Yeah. Yes. Thank you.
Okay.
Thank you. It looks like we need more observations of the partially melted and refreezing case.
Yeah, that would be kind of holy grail observations if we had these partially frozen particles and you could just slice through them and get a look, see how that ice shell is distributed around them and what the inside looks like. So.
Thank you.
Yeah.
Dana, we have a question from Megan. I'll just read it out loud in case not everyone's looking at the chat. Her question is, does your postdoc surrounding NWS messaging include any social scientists to best message crash concerns, or is that another topic entirely?
Yes, so that is not, that's not what I worked on, but that is like a couple steps down the road. We have I guess I could talk about it. We have a proposal that we're going to submit that includes some behavioral scientists, and we're going to kind of ask forecasters about when they start messaging road hazards leading up to events. So once that project is kind of underway, kind of the next step that we envision is to ask questions about, like what language might be better to use for motorists to actually adapt. Like if you say to slow down, are motorists actually going to slow down? Or what language would be more beneficial to getting a more desirable outcome, to make people stay off the roads, or also if they are on the roads, try to make sure that they're driving as safely as possible. So that is on our kind of horizon of what we want to look at, but I didn't look at that just yet.
Great, and we have a question from Zoe. She asked, have you looked at the relationship around visibility and precip type and how it might impact accidents?
Yeah, so we submitted a paper for like things that I did in the first year of the postdoc. So I did look at visibility and actually the change in visibility leading up to fatal crashes. And we found that not quite half, but maybe like 40% of fatalities had a significant reduction in visibility leading up to the crash. So we gave a threshold of at least 25% reduction in visibility. And that resulted in, again, about 40% of crashes had that reduction. But of those crashes, the visibility reduction was more on the higher end. So even though it met that 25% threshold, most of them were actually meeting a threshold of 50% reduction or a 75% reduction in visibility. So that is actually heavily tied to many fatal crashes that we looked at.
Thanks. That's the questions I see in the chat. I don't see any hands raised. While you're thinking of if anyone else has another question, I'll ask one, Dana. So in thinking about applying this, more broadly, in use of perhaps the NextRad radar network to be able to alert of these signatures, do you feel like the vertical resolution and the coverage of the radar data is sufficient to really get at some of the nuance of these signatures? And could you talk a little bit more about how you could relate that operational radar data set to these sort of alerts?
Yeah, so unfortunately, this is a very low level signature. So obviously we're kind of constrained to like a very limited range around the S-band radars with which we can actually potentially observe these signatures. Unfortunately, a lot of the times, these signatures are even lower than what we can observe with the S-band radars. So I know that's a very significant limitation here. I think one thing actually that we were interested in was, so more so from this work of looking at the microphysical modeling part of it, if we can constrain the modeling side of things using observations from radar, I think that's kind of where the larger and like broader impacts would be. If we can just better constrain the microphysics, we can better forecast, and not that we don't need the radar, but like it's always good to have the validation of the radar, but that way we can kind of fill in the gaps everywhere, and use the radar to validate. And I think that's something that's probably ring true for you. I think that sounds about right. Yeah.
Yeah, it's an interesting limitation. I just, yeah. Do we have any other questions? Yeah, I found something interesting in our own private discussion earlier that maybe the group would be interested in hearing, and some of the challenges of acquiring data sets. There's always challenges in data, and I just didn't know if you wanted to mention a little bit kind of your quest to get some of the accident data and how that kind of impacts your research and timeline. Maybe that would be helpful for others to understand some of those roadblocks.
Yeah, well, yeah, I guess pun intended with roadblocks. But yeah, so I for my postdoc, I wrote my own proposal, and it was intended to be a continuation of the crash risk analysis that I did. So to do the crash risk analyses, you actually need not just the fatal crashes, you need crash data for every single type of crash, the property damage only crashes, the injury crashes, including the fatal crashes. But it's a different data set than the fatal crash. So the FARS is available to anyone who wants to take a look at it. It's available online. NHTSA uses, they house the data. But to get the crashes themselves, you have to go to the state level. So if I wanted to get, Wisconsin crash data, I have to go to the DOT, and see if it's publicly available, or if it's not, who do I need to talk to get permission to use it? If I need permission, do I have to pay for it? I like to be pretty cheap in my research, so I don't like to pay for anything. But if I can just get permission to use the data, some states are very willing to give out the data. Other states like to hold it really close to their chest, so you can't get the data. So there's a little bit of limitation as far as where I'm able to get data and what I'm able to do with it. So that's why for the first year, I looked at the fatal crash data because I wasn't able to get my hands on the other data. So it can feel like a big hurdle to overcome, to not have what you really wanted to have at your disposal. But if you kind of take a step back and think it over, you realize that you can be successful using other data that's at your disposal, and it's not like the end all be all if you don't get exactly what you want at the time that you wanted to get it. So there's always something to do with the data.
Thanks for that, Dana. It's been really interesting to see what you've been able to do so far, and I look forward to seeing where you go with this. If there aren't any other questions from anyone? All right, well, if you think of anything later, I'm guessing, Dana, you'd be okay with some follow-up messages. And
yeah,
thanks again for coming and sharing your work.
Thank you.
All right, take care.